One area where Grignards and organolithiums differ is in the reaction with carboxylic acids. If you take a carboxylic acid and react it with a Grignard, you get an acid-base reaction. Essentially, because Grignards and organolithiums are both really strong bases. And a carboxylic acid is a weak acid. And so the carboxylic acid protonates the Grignard, and you get the carboxylate. The carboxylate is much more stable than the carboxylic acid, and as a result won't react any further until you add the dilute HCl and water, which forms H3O+, and that ends up giving you your carboxylic acid first. So essentially, no reaction has really taken place other than simply replacing this MgBr with an H. It's the same way with phenolithium. The difference between the two arises when you use excess phenolithium. What happens with the first equivalent of phenolithium is you get deprotonation of the carboxylic acid. You get the carboxylate. Now, organolithiums are much more reactive than Grignards. And if you have enough organolithium present, what you can actually do is add another R group to a carboxylate and actually punch through the carboxylate's resonance. Electrons go up. You get this O minus here, O minus here, in your R group that you added on. Now, this O minus cannot come down and kick off this phenyl group or this methyl group because that would result in a C minus, and C minuses are much more basic than O minuses are. It also can't kick off this O minus here because then you get an O2 minus, and that's really a strong base. And so this is essentially stuck until you add your acid workup step. But the first thing your acid workup step does is it goes through and finds any remaining organolithiums present, and protonates them, because it goes after their most strongly basic species first. Then it attacks one of these O minuses here. You get this O minus here. You notice this right here, it's a deprotonated hydrate. This O minus here can come down, kick this OH off, and you get your ketone. This ketone is not attacked by the organolithium because you don't have any organolithium left. It's wiped out by your acid workup step. So the key thing is why you can have a ketone survive in a Grignard or an organolithium reaction is that this ketone never sees and is never present at the same time this organolithium is. As a result, you can use this technique to form a ketone from an organolithium. You can form a non-symmetrical ketone where the two sides do not match. Now, the choice of the acid here. The reason I use dilute HCl up here is you need a little bit stronger acid to protonate a carboxylate than you do to protonate just a typical O-, because these have a tendency to be weak bases. So you need a stronger acid to protonate, and these are strong bases. And so you need a weaker acid. Could you use dilute HCl in both cases? Sure. Now, this up here, this carboxylate, Grignards do not have the power to react with a Grignard. You can add with a carboxylate. Even if you add excess to this, it still doesn't go further, and you still can't make this carbonyl group. Only the organolithiums have the strength to punch through the carboxylate resonance to go on through the rest of this mechanism.